Good afternoon, everyone. So it's really my pleasure to introduce today's colloquium speaker, Dr. Giada Arney. Giada earned her PhD in astronomy and astrobiology from the University of Washington, and her PhD thesis really focused on understanding how clouds can impact the habitability and the detectability of Earth-like planets. Then she won a NASA postdoctoral fellowship, which she brought at Goddard, and actually a number of recent awards that I want to mention. So she was one of the National Academy of Sciences Kavli Fellow in 2018. She received the NASA Early Career Achievement Medal in 2018. And then this year, she also received the Presidential Early Career Award for Scientists and Engineers. So congratulations. I know Giada through her work with the LUVOIR Mission Concept Study, which she's going to present today. And she was really a key member for the science case related to understanding how to search for biosignatures and to identify Earth-like planets. So I'm really excited to hear her talk and know how we are going to find another Earth. So let's welcome Giada.
Okay, thank you, Ilaria, for welcoming me and for inviting me here to Tucson. So Ilaria asked me to come here and asked if I would please speak about the search for life elsewhere with LUVOIR, which I was happy to do because this is a mission concept that I've been involved with for the past couple of years at NASA Goddard. So with that, I think I should spend a couple of slides at least mentioning what exactly LUVOIR is, since I know that a lot of you are planetary scientists and may not spend all of your waking hours thinking about potential future astrophysics mission concepts. Ooh. So LUVOIR is one of 4 large concepts that NASA headquarters directed the community to study in preparation for the 2020 Astrophysics Decadal Survey. LUVOIR is the perhaps most ambitious of these concepts. The other ones include HABEX, which is the Habitable Exoplanet Observatory. I also have a little bit of involvement with that team. There's also the Origins Telescope, which is a mid and far IR telescope. And then lastly, there's LINX, which is an X-ray observatory. So I will be spending my time now talking to you. I'm trying to figure out where to stand so I don't cast shadows on the screen. Talking to you about LUVOIR, which stands for the Large Ultra Violet-Optical-Infrared Surveyor. The large in LUVOIR does not lie, as you'll see in the next slide, how big these space-based observatories would be. We envision this observatory to be one in the tradition of Hubble, in that it would be an observatory with a similar wavelength range to Hubble from the far UV to the near IR. It would have a suite of imagers and spectrographs that I'll mention on the next slide. We would love for this observatory to be serviceable and upgradable, and we're building those capabilities into the observatory as we're designing them. Actually implementing them is the purview of the human spaceflight program, but we want to make sure that it could be done should the opportunity arise. And then lastly, it would have time allocation following the Hubble model, in that it would be a primarily guest observer-driven facility. So here's just a high-level look at LUVOIR. I'm not going to spend at all much time in this talk talking about the mission concept and the hardware. I'm not an engineer, I'm a scientist. So I'm a planetary scientist by training. I've actually worked on Venus as well, but mostly I've been working on exoplanets lately. Here's just a quick overview of what LUVOIR is. The big sister version of LUVOIR is called LUVOIR-A. It's a 15-meter space-based telescope. So its mirror is wider than this room is, probably. It's a very, very large observatory. And then the little sister to LUVOIR-A is LUVOIR-B, which is an 8-meter telescope. There are 4 instruments that we've studied for the LUVOIR study. ECLIPSE is the Extreme Coronagraph for Living Planet Systems. It's a coronagraph that would be designed to achieve the 10 to the 10 starlight suppression that you need to see an Earth-sized planet orbiting a sun-like star. LUMOS is a UV. Actually, it goes all the way from the far UV to 1 micron. It's a multi-object spectrograph and imager. with a resolution up to about 50,000. HDI is a high-definition imager. It's a wide-field camera with a 2x3 arc-minute field of view that goes from 200 to 2,500 nanometers. And lastly, Pollux. Pollux is a UV spectral polarimeter. It's a European contribution to the study that was led by CNES, the French Space Agency. These three would go on LUVOIR B. So B has bays for 3 instruments, A has bays for 4 instruments. Of course, if LUVOIR was actually selected, all of these instruments would be recompeted and restudied. So these are just notional designs for instruments that it could carry. I'm not going to be able to talk about all of the science that this observatory would be capable of, but I will give you a flavor of a little bit of some of the non-exoplanet science, since I'm sure there are non-exoplanet people in the room who might be interested in hearing about some of it. So here's one of our galaxy scientists' favorite example of a science case. So this is a low-mass galaxy at redshift 2. So the top panels have a galaxy with 10 to the 9 solar masses. The bottom panel is the galaxy at Z of 2, a redshift of 2, with 10 to the 6 solar masses. I'll zoom in now on the LUVOIR A panel. These small pieces of the galaxy have 30th and 31st magnitude, which I understand from our galaxy scientists is a big deal to be able to probe galaxy structure this faint and this small. So LUVOIR would be able to see the smallest building blocks of galaxies even at very high redshifts. Here is an illustration showing you how it might be able to detect very faint galaxies in the very distant universe. So the y-axis is in solar masses, in log solar masses. The x-axis is in units of redshift. Apologies, I think that was in white font and fell into the other white font. You can see that LUVOIR A and B would allow you to achieve observations of much fainter galaxies than we can currently observe. Just to tease a little bit of the solar system science, so here's Ceres, fabulous asteroid in our asteroid belt. It was observed by the Dawn mission versus a 2.4 meter telescope versus the 2 flavors of LUVOIR. You can really start to achieve observations of very small details, including that bright spot on Ceres. You can observe objects that are near and objects that are far. So here's what Pluto might look like to this observatory. You can see the heart on Pluto with both LUVOIR A and B. You might also be able to observe transient phenomena. So here's some simulations. Actually, the input observations for this were done by Hilda Ballister, who's located here. So this is what you might be able to observe of UV emissions from geysers that might be erupting from Europa. So one might be able to observe these geysers and characterize how frequently they erupt and where from on this moon. And then lastly, and this is my favorite example because I think this image is so stunning, this is an image of Jupiter from the Juno orbiter. It has 30 kilometers per pixel resolution. With LUVOIR A, you could achieve even better than that, 24 kilometers per pixel resolution. So this is already an incredibly spectacular image. So with an observatory like this, you could achieve flyby quality observations of a lot of the solar system. Okay, so that's just a teaser of some of the solar system science we might be able to do, but I'm not going to spend the bulk of this talk talking about those things. I'm now going to switch to talking about the topic that I'm most interested in, which is the search for habitable exoplanets and how we might infer signs of life from these planetary atmospheres. And a lot of what I'm going to talk about will be in the context of LUVOIR, but it applies more generally to searches for life with any observatory. So this is my holy grail, is I want to find Earth-like exoplanets. I want to find planets that are both habitable and inhabited. And I want to characterize them and understand them not as astrophysical point sources, but as actual complex planets. And in order to do that, we're going to need a lot of very powerful observations and a lot of observing time. Unfortunately, even with a telescope as powerful as LUVOIR or as powerful as the large telescopes that will exist on the ground, the extremely large observatories, will never get a spatially resolved image like this with those kinds of observatories. So instead, our images may look something more like this. This is a simulation of what our own solar system would look like if you viewed it at a distance of 12.5 parsecs distance. So this is simulated with the LUVOIR A coronagraph. The outer edge of the dark circle you see, that represents the outer working angle of the observatory, and it's wavelength dependent, which is actually causing the interesting different colors that you see on the outside of this image. The inner edge is where this overwhelming glare of the central star has been suppressed. So that within that, that's what we call the inner edge, the inner working angle of the coronagraph. The reason some people ask, why is Venus blue in this image, right? It's like kind of even more blue than Earth. The reason is because the inner working angle and also the outer working angle, they're wavelength dependent. They scale with lambda over d. So they scale with the diameter, they scale with the wavelength. Did not mean to hit that. The red wavelengths here are actually falling inside the inner working angle because Venus is so close to the sun. So we're only able to observe the blue wavelengths, and that is why Venus is blue there. This slide shows our anticipated yields of exoplanets with both flavors of LUVOIR based on our best estimates of exoplanet occurrence rates. These were calculated by Chris Stark at the Space Telescope Science Institute. He also did all of the exoplanet yield calculations for the HabEx mission concept. So if you are interested and look at those reports, you can really compare apples to apples. They were done with the exact same pipeline by the exact same person for the yields for those two missions. So for LUVOIR A, we anticipate observing about 700 exoplanets of all types. For LUVOIR B, we anticipate observing about 600 exoplanets of all types. For the ones I'm most interested in, these habitable planet candidates, based currently on our best estimates of eta-Earth that we've adopted at least for HabEx and LUVOIR, we anticipate observing about 54 planets with LUVOIR A and about 28 planets with LUVOIR B. So I should pause here and define what exactly I mean by a habitable planet candidate, because that can mean a lot of different things in a lot of different contexts. So what we mean by a habitable planet candidate, and again, this is consistent between LUVOIR and HabEx, is we want planets that are in the conservative habitable zone. So we're really trying to take a conservative cut in planet space here so that we can maximize our chances of getting at least a few, right? We don't want to under-design the capabilities of our observatory. We want to make sure that we're taking stringent cuts in parameter space so that we get, some number, and then if we get more, great, that's awesome. So we use the conservative habitable zone limits, which are these boundaries for a planet orbiting the sun. The habitable zone is the region around a star where you expect to have the possibility of liquid surface water. That is, liquid surface water is not strongly excluded in the habitable zone. The reason why we are so fixated on the water being on the surface when we think about exoplanets is because you need a surface biosphere, a global surface biosphere that's communicating with the atmosphere if you have even a chance of being able to detect that life across interstellar distances. If you had, say, an exo-Europa, yes, you might have habitable conditions under that icy shell, but you're not going to detect that life across interstellar distances, no matter how long you stare at it. So we really want the water to be on the surface. The planet has to be rocky. There's been studies by Leslie Rogers suggesting that planets greater than 1.6 Earth radii are not rocky. They are, in fact, gaseous mini Neptunes. We take a conservative cut at 1.4 Earth radii. So everything smaller than that we are okay with, but then we don't want to go too small because then the planet might not be able to hold onto its atmosphere. So you need something that's big enough and far enough away from its star to be able to hold onto a long-term substantial atmosphere. And for that we use Kevin Zonley's creatively named cosmic shoreline, which is the region and parameter space for planets of certain sizes and distances from their stars at which you would expect them to be able to hold on to their atmospheres over long timescales. A question that we want to be able to answer with this type of facility is how common habitable planets are. You've probably heard news reports suggesting the discoveries of potentially habitable planets like the TRAPPIST-1 system or Proxima Centauri b, et cetera, et cetera, et cetera. These are rocky planets that are in their star's habitable zones. But unfortunately, currently, we know so little about these planets. We know information about their sizes, we know information about their planet-star distances, and that's pretty much it. we don't actually know whether these worlds are truly habitable. And just because you're in the habitable zone doesn't mean you're habitable, right? We have no idea yet what the frequency of true habitability is. So having large sample sizes maximizes our chances of getting lucky. Let's say habitability is rare. If you observe, let's go back. If you observe 54 candidates with LUVOIR A, then what that means is that if the frequency of habitable conditions was only 5%, which I'm an optimist and I think that's probably too low, but if it was only 5%, then that size sample would guarantee you seeing at least one truly habitable planet and 95% confidence. What I think is more interesting, at least from this perspective of large numbers, is to consider what happens if habitability is really rare. What happens if we get unlucky and habitable worlds just aren't common? We find all these planets that are rocky and in their habitable zones, and maybe none of them have atmospheres. I don't think that's likely, but in that case, large sample sizes mean that the null result is also statistically interesting, because in this case, 54 candidates would allow you to constrain the frequency of habitable planets to less than 5% and 95% confidence. So for the first time, we can actually when I was at the Astrobiology Science Conference earlier this summer, I love the way one of the people there put it, which is that with statistics like this, you can actually start to put meaningful numbers on some of those terms in that Drake equation, you know, where people just wave their hands and totally make stuff up. So finally, we can actually start to say, oh, we actually know something about the frequency of Earths out there because we've actually measured it. We've done this experiment. With 28 candidates, you can do that to 10% and 95% confidence. So with these large sample sizes, it will be thrilling to discover how rare or maybe common true Earths are. Okay, so we don't just want to, of course, count these planets. We want to actually characterize them. To do that, of course, we're going to be taking their spectra, and of course, this is also how we're going to determine whether they are truly habitable. The metric that we have for letting something rise from the level of a habitable planet candidate to something that we think might actually be Earth-like is we want to look for water, because water is central to our definition of planetary habitability. So anything that has water vapor in the atmosphere, we consider something that's worthy of future, very, very detailed study. And things that we think might actually be habitable, then we want to look for inhabitants. We want to see, could these planets actually have life? And this is something that myself and my colleagues and tons of people in the astrobiology community have spent so much time thinking about how we might do this. So this is a spectrum of modern-day Earth. The canonical biosignature of modern Earth is oxygen, and its photochemical byproduct ozone. Oxygen is the byproduct of the dominant metabolism on our planet, oxygenic photosynthesis. We think it evolved quite early on in the geological record of Earth, but for reasons that I will talk about later, we don't necessarily think that it's the only biosignature that we should be going after. Another biosignature that you might be able to go after for the spectrum of modern-day Earth is methane. Most of the methane in Earth's atmosphere that we're breathing in right now, on the order of 1 part per million atoms that we breathe in is a methane atom. Most of that is biological. So biological production of methane on modern Earth outweighs abiotic production at a rate of about 65 to 1. So lots of biological methane production going on. With a direct imaging mission where you're observing reflected light, you could also look for surface reflectance biosignatures. So various kinds of interesting pigments might exist that you might not be able to match to any sort of known mineral compounds. That might not be definitive, but that might be suggestive. If you see surface reflectance biosignatures that you don't understand, also together with atmospheric biosignatures. A wrinkle that I want to emphasize is what you actually get from a spectrum versus what you actually want to determine or think about whether there's life there. From the planetary spectrum, you can retrieve gas concentrations. So gas concentrations, the amount of gas that's in the planet's atmosphere, is a retrievable quantity from the spectrum. But these gases in a vacuum, just in and of themselves, like they're interesting, but they're not themselves the biosignatures. just knowing that oxygen is in an atmosphere is not enough to tell you that there's life there. Every single biosignature candidate that you can think of, you have to consider it in the full context of the planetary environment, as well as the stellar context, because the photochemistry that these stars can drive can really change the compositions of their atmospheres that are possible. If you take all of this information, so your retrieved concentrations, which will probably have large error bars, together with as much information as you can gather about the planet itself, you can then feed these into models to get the holy grail, which is gas production rates. This is really powerful if you can find this out, because production rates that are unexplainable or difficult to explain through abiotic processes alone can suggest the involvement of biology. So if you see a planet like modern Earth, if you were able to back out the concentrations of oxygen and methane in modern Earth's atmosphere, you would realize, like, whoa, these are being produced insanely rapidly, way more rapidly than we can plausibly think of abiotic processes being able to support. And so therefore, that's suggestive of life on our planet. So this is the kind of game that we want to do for exoplanets. And this will require very high signal-to-noise observations. So here's a spectrum of Earth. So this is Earth arbitrarily placed at 7 parsecs away around a solar twin star that doesn't exist at 7 parsecs for observations that take 35 hours versus 120 hours for LUVOIR A and B per coronagraphic bandpass. Here are the biosignatures that one might go after for our planets. So I've walked you through these before. So ozone, which is a photochemical byproduct of oxygen. Here's another oxygen feature in the near infrared, and also methane, which produces a weak absorption feature. I'll talk more about methane later on. You'll also notice that our spectrum is awash in water features, which is great because, again, that's a really important planetary property that we want to try to go after. But modern-day Earth is just one data point, and the biosignatures of modern-day Earth is really, I think, limiting if this is all we think about when we think about detecting life elsewhere. I've spent a lot of time, and some of my colleagues have spent a lot of time thinking about how we might use Earth through time to help broaden our perspective of the kinds of life we might seek elsewhere. Earth has gone through a lot of evolution over its history and has presented to would-be alien observers who might stare at our planet at different phases of Earth's history very different prevailing environmental conditions and very different dominant biospheres. So even though this is still just one planet, it's a lot of more examples of different kinds of biospheres that we might be able to go after. So I think using Earth through time to help at least guide our perspective of beginning the search for life elsewhere is really, really powerful, because these are planets that are by definition Earth-like, because they are literally Earth, but at least they're different from modern-day Earth. The canonical biosignature of Earth, oxygen, has not always been detectable from our planet's spectrum. In fact, it's only been detectable for a small fraction of our planet's total history. Here is a timeline of Earth's history, and here in the bottom panel is the history of oxygen in our atmosphere from a review paper by Chris Reinhard. It cuts off at the beginning of the Archean because we frankly have almost no geological record of the Hadean, but we don't think there was any oxygen in the Hadean either. You'll notice oxygen has only been at present in our atmosphere at high abundance for a small fraction of our planet's history. During the Phanerozoic, there's gobs of oxygen. So this is modern Earth, when we have an atmosphere with about 21% oxygen. That makes it very nice and easy to detect, relatively speaking. But in the Archean and Hadean, which represents about half of Earth's history, our atmosphere is anoxic, and you wouldn't be able to see it in the spectrum at all if you were looking for it. So if you were an alien who was short-sighted enough looking at Earth and you were only looking for oxygen biosignatures, you would falsely conclude that Archean Earth was not inhabited, which is obviously not the case. And there's been suggestions that even in the mid-Proterozoic, even after the rise of oxygen, oxygen levels may have actually been quite low, making oxygen very difficult to detect. So what I'm telling you here is that you can't just rely on this one biosignature. Even though it's a great biosignature for modern Earth, it's not going to work if you're thinking about other kinds of planets. And given that Earth's atmosphere was anoxic for about half of our planet's history, we really need to think about how to detect life on anoxic planets as well. I mentioned methane earlier. methane, I think, will be a really important gas for trying to understand if there's biology in anoxic environments. Most of the biological methane in modern Earth's atmosphere is produced by a very simple type of metabolism called methanogenesis. Methanogenesis, we think, evolved very early in the geological record, perhaps as early or earlier than 3.5 billion years ago. It's a really simple metabolism. It takes carbon dioxide and hydrogen to make methane and water. The dominant abiotic source of methane on Earth is serpentinization, the hydration of ultramafic or iron and magnesium-rich rocks at the seafloor. So serpentinization, when you hydrate these types of rocks, you get a green mineral called serpentine, as well as methane as one of the byproducts. And this is where most of the abiotic methane in our Earth's atmosphere comes from. So people have tried to think about how far can you push serpentinization in terms of methane production? My friend Josh Chrysanson-Totten, he ran a model where he controlled different parameters that go into serpentinization, like, for example, the rate of seafloor spreading, the fraction of the crust that's composed of these ultramafic minerals. He allowed these parameters to vary over ranges that at least he considered reasonable. And when he does this, he gets this curve here of different methane fluxes. The probability of these different methane fluxes being able to be produced by serpentinization on an arbitrary planet. The important thing to notice here is that the rates of production of methane by serpentinization are less than the rates of production that, at least on Earth, we get from biology, both for the modern biological flux and estimates of the Archean methane flux. So again, this is going back to this idea of flux rates being the true biosignatures. If you were to measure a planet and back out a methane flux production rate of something like 40 teramoles per year, that would be incredibly interesting, because you would think that that might be really difficult to explain through a process like serpentinization. Versus if you were to look at your planet and say, well, you only need like 5 teramoles per year of methane in this context to produce the amount of methane we see, that's definitely something that serpentinization might be able to explain. So maybe that's not life in that context. For Earth, modern-day Earth needs a really high methane flux to explain the amount of methane in its atmosphere. So in this context, methane is, of course, a biosignature. Here's a possible spectrum of Archean Earth. I've highlighted the CH4 features here. I've also boxed in a CO2 feature here. Methane in the context of an atmosphere containing CO2 also needs more rapid production rates, not as fast as in the context of an atmosphere containing oxygen, but oxygen radicals that you can get when you dissociate CO2 can destroy methane. And so having a spectrum that looks like this is a very different spectrum from modern Earth. There's no oxygen here, but you could still infer that there might be life on this planet if you can back out the concentrations and then try to infer something about the fluxes that are producing these gases. So lots of methane and lots of CO2 together in an atmosphere can point to high methane production rates, which would be really interesting. I also want to point out that you get a lot of really strong methane features for a planet that has an anoxic atmosphere like Archean Earth, which makes methane a lot easier to detect. So for modern Earth, the only methane feature you can see is out here, but here you can see lots of methane features, almost sort of pushing into the visible part of the spectrum. But again, remember, if you remember one thing from this talk, it's that biosignatures have to be interpreted in the context of their environments. Titan, Saturn's moon, has lots of methane, right? Something like 3 to 5% methane. But in that context, is that methane a biosignature? I think most people would say no. And part of the rationale why they would say no is you don't need life to explain the amount of methane you see, right? You can do it through other processes like clathrates degassing the methane into the atmosphere. You don't need incredibly rapid production rates that are difficult to explain through abiotic processes. Another dramatic feature of Titan is its haze. So this haze has completely transformed how we view Titan from across interplanetary distances in our solar system. And if you were to view a hazy exoplanet, well, it would completely change your ability to study it across interstellar distances. Believe it or not, there's geochemical records, there's geochemical evidence suggesting that in the later part of the Archean, we may have had a haze in our own atmosphere, a global organic haze, orange in color, similar to the one that's in Titan's atmosphere. There have been people going into the geological record. I'm not going to go into the details of this because I don't have time and it's not the topic of this talk, but I'm happy to talk in more detail about how exactly people have inferred this haze from geochemical evidence. But needless to say, people have. There have also been studies that have looked at this haze from a laboratory perspective as well as a photochemical modeling perspective. And both types of studies suggest that if you were to have in the early Earth's atmosphere a methane to CO2 ratio greater than about 0.2, that can trigger the formation of one of these organic hazes. And these hazes would dramatically change the habitability of our planet, the spectral appearance of our planet, et cetera, et cetera, et cetera. Like, I've given literal entire talks on this topic. I only have like 2 slides here, but it's, I think, a really interesting type of planet because this is arguably, to me, the most alien phase of Earth's history. So when we talk about looking for alien exoplanets, this is hazy Archean Earth. It is arguably the most alien planet we have geochemical data for. We know it was habitable. We know it was inhabited. So hey, let's study it in the context of alien exoplanets. So here's what early Earth might have looked like with a haze. Here's this beautiful organic haze absorption feature that hangs out at UV blue wavelengths. So this is the reason why Titan is orange, because all this blue light is getting absorbed away. It's also a great UV shield. So from a habitability perspective, these hazes can actually perhaps enhance the survivability of life at or near the planetary surface for the planets that they exist on. So here's lots of methane in the spectrum. Again, here's CO2, which in this context is really important. Knowing the redox state of these atmospheres is really, really important when trying to understand the fluxes of the methane that might be produced. And as I mentioned before, methane in the context of detectable amounts of CO2 can be a biosignature because it can point at high methane production rates. Haze as well, which produces this ridiculous huge absorption feature in the context of an atmosphere containing CO2, again points to high methane production rates that might be challenging to explain through abiotic processes alone. So I like to think of haze as a novel, non-gaseous biosignature in some contexts. Okay, so moving on to Earth's middle history in the Proterozoic. So this is after the rise of oxygen. The mid-Proterozoic here, it's been suggested in a couple papers by Noah Planowski that the mid-Proterozoic may have only had something like 0.1% of the modern atmospheric abundance of oxygen, which is challenging if you want to directly detect that oxygen because you can't, at least not with reasonable integration times and reasonable signal-to-noises that you might try to go after. So in that case, what do? Well, you turn to its photochemical byproduct, ozone. So ozone is a wonderful gas because it produces an absurdly strong absorption feature at UV wavelengths. This feature is so strong that it can become detectable even when the oxygen itself, which would otherwise be absorbing here, is not detectable. So this is a ridiculously strong UV cross-section that ozone has here. Because LUVOIR has allowed Earth's history to guide our design of the coronagraph, this feature here has really allowed us to argue for keeping the UV capabilities of this coronagraph, even though they make the instrument more complicated. So constantly during these studies, there's all these trades that always happen between the scientists and the engineers. And the engineers are like, UV coronagraphs are really challenging. Do you really, really need this? And we're like, yes, we really need this because we want to detect ozone. Because for a large fraction of our planet's history, this may have been the best biosignature that one could go after for a low oxygen planet. You might also be able to get methane for a planet like Proterozoic Earth. There was a recent really interesting paper by Stephanie Olson where she was thinking about Proterozoic ozone levels in terms of an interesting kind of seasonal biosignature. So this plot is showing, so the purple spectrum here shows a spectrum with a modern-like ozone abundance. And then these values here shows what one might get from seasonal variation in oxygen production. You get seasonal variation in oxygen production on Earth, but it doesn't do anything to the spectrum because this ozone feature is totally saturated. But for a feature like Proterozoic Earth may have had, where the feature is not saturated, you can actually get quite dramatic changes in the strength of that feature from small changes in the amount of oxygen and therefore ozone in the atmosphere. And so this might be a really interesting temporal biosignature you could go after if you observe the planet over its orbit. A sort of more general way of thinking about certain types of biosignatures is you want to try to find atmospheres that are in chemical disequilibria that you can't explain through abiotic processes. So the oxygen and methane together are this canonical disequilibrium in our atmosphere that's been pointed out all the way back since the 1960s by Hitchcock and Lovelock. These two gases together are an extremely robust biosignature. Again, it's because together they imply very rapid production of both of these gases. That's probably more rapid than any abiotic process that we can dream up. But a tricky thing, like a dirty secret of Earth's history, is that it's actually really hard to detect these gases together. For modern day Earth, when we only have about 1 part per million of methane, it's going to be challenging to pull that signal out of the spectrum. There haven't been enough retrieval studies that have actually quantified how difficult that will be, but I assure you it will be a challenge that we will only do on the most wonderfully interesting targets. But you do get ozone and you do get O2 relatively easily. For the mid-Proterozoic, depends how much methane there was. It might have been challenging to detect that as well. We're not certain. But O3 is certainly going to be more easily detectable than O2 if indeed O2 levels were as low as has been suggested. And then for the Archean, before the rise of oxygen, well, methane's pretty much all you've got. But this is true only for a particular planet orbiting our sun, right? So this photochemical context that I've just described to you is for our own planet, but exoplanets are going to orbit stars of zillions of spectral types and have different photochemistries. And this is really critical when thinking about the kinds of biosignatures that one might expect to occur on exoplanets orbiting other kinds of stars, because photochemistry is super critical. So going back to LUVOIR, so LUVOIR will be observing planets orbiting mostly FGK stars, a little bit of A stars. About 10% of the sample is M dwarfs. And all these different kinds of stars will have all their own unique kinds of photochemistries. And photochemistry, if you take one other thing away from this talk, it's that photochemistry is really critical when trying to think about biosignatures. And I'll give you an example here. So this is what happens if you take the Earth and you put it around an M dwarf. So mixing ratio is jargon that atmospheric people use a lot of the time. It just means the fraction of the atmosphere that's composed of methane. So this is the fraction of the atmosphere composed of methane as a function of altitude. For modern day Earth, this is exact modern day Earth orbiting the sun. We only have about 1 part per million of methane for modern day Earth. If you take literal exact Earth with the exact same source fluxes and the exact same amount of oxygen in the atmosphere and you put it around an M dwarf, so here's your different M dwarfs, AD Leo and GJ643c. Wow, like you get 2 orders of magnitude more methane in that photochemical context. The reason is because these M dwarfs produce less radiation in the part of the spectrum, around about 300 nanometers, where you dissociate ozone. And oxygen radicals produced by ozone photolysis are the dominant sink of methane in an oxygenated atmosphere. So if you don't photolize that ozone as rapidly, or if you photolize it a lot less rapidly, as is what's happening here, your methane photochemical lifetime can increase by orders of magnitude. And so the kinds of biosignatures that you might anticipate being able to observe in an oxygenated atmosphere are different around M dwarfs as compared to G dwarfs, because methane is really easy to go after around these kinds of stars, but might be much more challenging for modern day concentrations for modern Earth-like planet around a sun-like star. So as I mentioned, about 10% of LUVOIR's target list will be M dwarfs. I was interested in exploring the same phenomena for K stars, which represent a higher fraction of LUVOIR's target list. So K stars, like M dwarfs, also produce less radiation in that critical part of the spectrum where you dissociate ozone. So here are some examples of atmospheres with different methane fluxes going into the atmosphere at the bottom and different oxygen mixing ratios. Again, that means the fraction of the atmosphere composed of oxygen. And when I run a photochemical model, what I find is that I can generate about an order of magnitude more methane around a K6 star. So this is one of the K dwarfs in the Mussels stellar catalog compared to around the sun. So it's the same phenomenon that we see around M dwarfs. It's not quite as much methane as M dwarfs accumulate, but it's still enough that you get a big detectability bump, which is great. Here's some representative spectra of the planet around the sun versus a planet around a K star. The teal spectra have all of the gases included, and the orange spectra have the methane removed so that you can clearly see where it's absorbing, and you get these wonderful, beautiful absorption features from methane much more strongly for this planet around the K star. Another reason why I really like K-stars is because they're dimmer than the sun, and so what that means is that you get better signal to noise in the same integration time because the planet-star flux contrast is not so high. Here are some real stars that are nearby that we might go after with LUVOIR or some other mission. Here are their actual distances, so you can compare stars of comparable distances, and what you can see is that these K-dwarfs always have higher signal-to-noise at 1.04 microns that I picked to represent the signal-to-noise that I printed on here. So K-dwarfs are wonderful, both because they might allow you to more easily detect oxygen-methane disequilibrium biosignatures, and because you don't need to integrate on them as long to get good signal-to-noise. Lastly, I just want to talk briefly about how LUVOIR will observe a diversity of worlds, and I have no idea how I'm doing on time. So LUVOIR is going to observe lots of exoplanets. I will remind you that we're not just doing Earths. So I've talked a lot about Earths because that's what I really am interested in. But remember, for every one Earth we get, we're going to get 10 times as many other kinds of planets. And undoubtedly, we're going to get surprised because every time we look for exoplanets and characterize exoplanets, we discover things that we never guessed could exist out there in the universe. I think the powers of these large samples will be really amazing when we try to detect life elsewhere. So when we observe these potentially habitable exoplanet candidates, and if life is rare, having a lot of candidates maximizes our chances of getting lucky. I don't know how lucky you feel, but I don't know how common life is out there. And I would love to get some positive identification of biosignatures on an exoplanet. So I want as many planet candidates as I possibly can get. So maybe we'll get lucky, and maybe we'll even get lucky on more than one target. What I think will be really, really amazing is that if we detect potential biosignatures on more than one planet, we can begin to actually do not just comparative planetology, but comparative astrobiology, which is mind-blowing. We can't do that right now. That's so far away from now, but maybe someday. And I also think it's powerful because if we can detect biosignatures on more than one planet, maybe some of those are false positives. Maybe some of those are explainable through abiotic phenomena that we haven't thought of yet. But if we see them on multiple targets, that might increase our confidence that at least some of those planets are true positives. Ooh. Or maybe we'll find out that life is really rare, and that will tell us just how precious Earth is in our universe, because we'll actually start to be able to, again, put an upper limit to the frequency of Earth-like planets that are out there. Also, the power of large numbers is that it will allow us to sample the full diversity of worlds, not just habitable planets. We'll be able to look at Jupiters and Neptunes and mini-Neptunes and super-Earths, planets that are hot and planets that are cold, and compare them to each other within and across systems. Here's a dramatic example of the power of observing multiple spectra of a same class of planet. So here's a famous plot from a paper by David Singh, where they observed transits using the Hubble Space Telescope. And then here are some models plotted behind the data. And lo and behold, hot Jupiters look different from each other. Amazing, which we should expect, right? We should not expect them all to look the same, and they don't. So we're already beginning to do this kind of science on the low-hanging fruit targets that are the easiest to observe. Here's, just for fun, for the people who like transits in the room, here's what one transit of LUVOIR could get on those planets. So pretty good data. All right, so I want to end now with what I think is a really beautiful quote from the recent National Academy of Sciences Exoplanet Science Strategy Report. The search for life on other worlds is both a profound and profoundly difficult endeavor, but what's really exciting is that we're finally on the cusp of actually being able to tackle the question, are we alone in the universe, from a scientific perspective. We almost have the tools to be able to do this, and it's really thrilling to live in a time when an observatory might fly and might actually answer that question. So I still have no idea how much time I have left, but I will take questions now. Thanks.
Thank you very much for the nice talk. So questions,
I wanted to ask about the observing strategy for LUVOIR. So there's this initial survey, and will you already gain some information on whether the planet has an atmosphere during that, or will you have to do follow-up observations for every planet that you identify to even be say, at least maybe not detect biosignatures, but be able to rule out different planets?
Good question. So during the initial planet search phase, so LUVOIR will be searching for these planets, by the way. They will have to be found by this observatory. It will be taking chunks of this, not complete spectra, but chunks of the spectra. What you can do with the coronagraph is the coronagraph has 3 channels. One is the UV channel, one is the visible channel, one is the near IR channel. You can observe in 2 channels simultaneously. You have to use the 3rd channel for wavefront control. So 2 channels are free for you to play with. One of the band passes that we will select will be in I think it keeps switching between the visible. It switched several times between the visible and the near IR channel, depending on how we make that cut in wavelength space. I think it's currently in the near IR channel. So we want to center one of them on the 960 nanometer water band. The reason why we want to do that band, if I can back up several slides. Let's see. So we are going to look at this feature here. So this water band is particularly useful because, well, it's a strong feature, but also importantly, it's not completely overlapped by methane. Methane has this pathological tendency to overlap with water features. So if you were to look at, say, the Archean Earth spectrum, which I'll scroll to, let's see, here's Archean Earth. Let's see, so methane and water, yay, methane and water everywhere. These strong water bands in the near IR, we don't want to use those for our initial search for water because it could be methane, which would also be interesting, but our initial search, we really want to target water. So we pick this feature here, both because there's water and because there's an adjacent but not completely overlapping methane band. So you could potentially get water and methane in the same initial observation that you're using to simply search for the planets. So that's one band pass. The other band pass that you could pick some other wavelength. So assuming I'm remembering correctly that this is now in the near infrared channel because it has changed so many times, you would probably pick your second bands over something interesting like the oxygen feature in the visible part of the spectrum. Or if I'm misremembering, and this is now in our visible channel, you'd probably pick some interesting methane water feature in the near infrared to go after as your second channel. So you will get information during the initial planet search about the atmospheric composition. It will not be a full spectrum, though. You're primarily searching for water in that phase, but maybe you'll also discover some biosignatures, potentially. They'll be very low resolution spectra, though. So
the atmospheric retrievals are very interesting, but most of the planets that LUVOIR targets are not going to be translated.
that's right.
And so what kind of priors are necessary to actually interpret the spectra that you get?
Yeah.
How are you going to go about getting those priors?
Yeah.
What precision do you need?
Yeah, I keep wanting there to be more. If anybody in this room is a retrieval person, please do more retrieval studies on not just the visible part of the spectrum, not just water, not just ozone, not just oxygen. just my, what I would love. So things that we want, yes, you're right. Most of these planets will not be transiting. Even if they are, we're not going to be getting data from a planet transiting a G-dwarf, if that's what we're trying to observe, because they're not going to transit frequently enough. The transit depths will be so tiny, even LUVOIR will not stand a hope of doing them. So for thing that we are going to be doing is LUVOIR carries on board an instrument. So one of LUVOIR's science goals is to actually measure the masses of planets using astrometry. So it's going to be part of this initial Exoplanet Science survey. That data will be actually precise enough to be able to be used for astrometry. Doing the initial planet search, we observe these targets multiple times because you can't just observe them once, because in that case you're vulnerable to false positives like background star contamination, might look like a planet, et cetera, et cetera. So on average we'll be observing each system about 6 times. So you can actually start to measure the orbit. That's what we've calculated is enough to start to place constraints on the orbit. So I don't remember off the top of my head what exactly the precision is. It's in our report. It's in chapter 4 of the report and also in the appendix. Yeah, go ahead. Yes, yes. Yes, to measure the masses of Earth-sized planets with astrometry. If you want the details, we have a 460-something page report plus a 460-some page appendix.
What is the spatial resolution?
The spatial resolution? Oh God, you're asking me hard questions. Yeah, I mean, it's sufficient that you can resolve these point sources, first, that you can resolve the planet from, obviously. I don't recall what the spatial resolution is. I know that we're Nyquist sampled in the visible. Yeah, we're Nyquist sampled in the visible with the HDI instrument.
In the previous figure, you had a comparison with the Decadal data, and you said you could get all that with one transit.
Try to go back to that. Trying to find it. Here we go.
So what kind of spectral coverage do you have where you kind of cover all that in one transit, right?
Yeah, that's an excellent point. So this would be observed with the HDI instrument, where I'm much more familiar with Eclipse, which is our coronagraph, than I am with HDI. I suspect that when Eric says this needs one transit, it's one transit per chunk of the spectrum. But it's still really fantastic data. Yeah.
And also, for this data, we had the problem that when you optimize the CCD for responding better in a spectral region, the longer wavelength regions are fringing. And for HST, we thought we could take care of that fringing, but we couldn't. And what we found is for brighter and brighter stars, the fringing effect was worse. So I don't know how you guys talk about these types of effects.
I don't.
It's the major problem.
Yeah. That's an interesting point. I don't think that was included in this model. Yeah, but that might be something that would need to be considered. But certainly, even if it's not one transit, you get quite high signal to noise in a much shorter amount of time than you would need for Hubble.
And you should check because you like the quarter band.
Yeah. That's the valley of death for CCDs. Okay, it also has really bad quantum efficiency. Yeah. Okay, yeah.
Pay attention to that one.
Yeah, I have a question about, I discussed for lunch that the launch date would be 2039, something
Mm-hmm.
So is there technology for these already on there?
Mm.
Or
No, it is not. So that's part of why it can't launch more quickly than 2039. A large effort has been devoted to thinking about what are ways that one could mitigate cost growth on telescopes and help them to launch in a timely fashion. One of the ways of doing that is to do a lot more technology development up front. So this is in a phase of the mission that would be called pre-phase A of the mission. So before it gets the okay from NASA to like, proceed, you're awesome, keep going, do a lot more dedicated technology development to mature your technologies that are critical up to a threshold. So NASA thinks in terms of technology readiness levels, which is, I'm trying to think of the analogy. So like TRL 0 is like you've thought of a unicorn, and TRL, I forget what they are. TRL 5 is like maybe you stuck a horn on a horse, and TRL 9 is you've launched a unicorn into space, right? So these different technology readiness levels. So what people want to do and what we argue is that if you could mature the technologies to TRL 6 before pre-phase A, that mitigates a lot of the risks that are associated with having non-mature technologies lingering later on into the mission development life cycle. So you really want to try to do a lot of the tech development as early as possible in parallel with each other, so that these different technologies that need to be done in parallel and talk to each other can inform, the whole process. So I think that was a long answer to a question, but did that answer your question?
yeah.
Okay, great.
I wonder if you comment if the possible availability of a star shade would substantially change the capabilities of operational.
I might have a backup slide on that, but I'm not sure. Okay, so it's not exactly answering your question. So we looked at star shades for LUVOIR. So this is showing how the yields would be impacted for different types of coronagraphs, and also for a star shade. So here's LUVOIR A, here's LUVOIR B. You have to use different kinds of coronagraphs for the different kinds of telescopes that LUVOIR A and B are. So LUVOIR A is baseline to use an apodized pupil Leo coronagraph. LUVOIR B is currently baseline to use what's called a vector vortex coronagraph. They both have their own challenges and opportunities associated with them. Star shades, I think HabEx was really smart in that they picked a mission that uses both a star shade and a coronagraph for their baseline concept, because in the size regime that HabEx is, I think that really allows them to maximize their yields, because a coronagraph alone or a star shade alone I don't think would be as compelling as a mission concept as using both of these together are. So I think that was fantastic of the HabEx team for doing that. What's tricky though about star shades for large telescopes is that the size of the star shade is proportional to the size of the aperture, so that if you wanted to get all of the wavelengths for an observatory that's say the size of LUVOIR B or LUVOIR A, your star shade has to be enormous. So we looked at that. It's described in one of our appendices in the report. So if you're really curious, you could open up the appendices. We have a description of the star shade exploration study that people did. In general, I think we decided for now a star shade would not be too feasible with LUVOIR, simply because it would be too big. However, you could also think about star shades that didn't do all the wavelengths. So you might do a UV only star shade, for example, which would need to be much smaller. Maybe that would be feasible. But I don't think a star shade alone, you would be able to do it. You'd want to use a star shade and a coronagraph for LUVOIR as well, because they both have different advantages and different disadvantages. Together, I think they're very powerful.
So I think we are at the end of the time. If there are no more questions, then let's